Thank you, Florian. Thank you for your nice introduction and the invitation to participate again in this very nice event. And let's see if people is interested in some information about EMI. I will try to explain things about EMI and how inductors can increase our problems. Inductors usually are basically very important in designing filters and different solutions for EMI problems, EMI and EMC problems. And sometimes they are the origin of our. Well, let's see if we start here. So like Florian was explaining, I am at the University of Zaragoza teaching EMI and radio frequency topics, and now I have a company, a spin-off of the university that is working in this kind of topics. So you are free to contact with me and to visit my laboratory in Zaragoza. So in the slide you have the description of my contact and the CV. So let me know if you are interested in something in special. Well, we will be talking today about inductors. How inductors are usually considered when designing in radio frequency or in EMI. And we will try to work with a buck converter. I will try to make some measurements. We will be using the both F500 to evaluate how the inductor can be or not dangerous for us. We will discover that with both 500 we are able to create very nice models for simulation, for example, using LTSPICE. I will be using LTSPICE, and at the end we will have some conclusions. So let's start with the idea, no? Inductors. Inductors are everywhere today in electronics. For example, you have inductors when you are working with analog filters, analogs for signal processing, no? These kind of inductors can be with or without core, depending on the frequency where you are working. Or for example, you have inductors when you are trying to solve EMC problems, conducted emissions problems. You can have differential mode inductors like this one, or you can have common mode inductors like this one, depending if you are interested in filtering differential mode or common mode emissions, okay? Obviously, remember that these kind of filters are useful too for immunity. Or for example, you have inductors when designing a specific topologies like PFC circuits, power factor controllers, so where you have typically inductors in big size with core, and in this position here, they are very critical for to comply with the limits in harmonics in the consumption, in the current that your product is consuming, but additionally they can create problems in radiated emissions. And finally, we have, for example, DC-DC converters or topologies, no? Where in this example, we are seeing a back converter and the typical inductor in the output of the converter. Remember, I am not explaining here nothing about transformers, but transformers can be analyzed in a similar way like I will do with inductors. So let's consider the ideal inductor. Consider that you take a piece of wire and you create several turns, and you have something that in your mind is something like this. You are thinking you have one inductive effect. Remember, inductive effect means that you have an impedance that is omega L, and phase is 90 degrees. So if you are interested in plotting how is the response of this component, you will do something like this. For example, you will take a line in this orientation, and this is omega L. Look at this, the impedance starts in 0, because at omega, a frequency equal to 0, you don't have ohms, and is increasing in omega L. The phase for this component, in theory, is something like this, is 90 degrees. So this is our ideal response for the inductor. What happened in a real inductor? In a real inductor, we can plot something like this. In some specific low frequency range, the inductive effect in the real component match the value of the ideal component, and in high frequencies, the component starts to decrease the impedance. No, the decrease in impedance is because of a capacitive effect. The capacitive effect is easy to find because the phase of the component goes from 90 degrees to minus 90 degrees in this position, no? This is minus 90 degrees. So this is the area where the component is inductive, and this is the area where the component is capacitive. Why you have capacitance? You have capacitance because usually we have capacitive effect between the windings, okay? And this is what we call the self-resonant frequency of the component. So usually we work with inductors in this area. It's in the area where the component is inductive, and we avoid components where the self-resonant frequency is close or below our working frequency. So something that is very important for designers in inductors is this sentence. The ideal behavior of an inductor is a fantasy. Its parasitics define your EMI and EMC reality. So when we go to an inductor with core, we go to an inductor with core when we want a lot of value of inductance, I mean microhenries or millihenries, and we want to avoid a very, very big inductor. An air core inductor offering hundreds of microhenries or millihenries would be really, really huge, really, really big. No? So usually in our model of the inductor previously, we could draw something like this. We can consider that the real response of the inductor could be something like a resistive effect because of the wire resistance, the inductive effect, and the capacitive effect that we have between the windings. This is a parallel resonant circuit. So if we go to the inductor with core, usually the model in high frequency is the same. It's an resistive effect that is related with the wire, the inductive effect, the parasitic capacitance, and the parasitic resistance that usually is considered modeling the losses in the core. No? Usually it's a resistive value of hundreds of Ks, perhaps megohms, depending of the losses in the inductor, and the small resistor here is related usually with the how long is the wire you are using for the conductor and how is the diameter of the wire. Okay, so usually this is the way we work with inductors. We consider how much is the inductive value we need, and we try to know how is the self-resonant frequency of the component to avoid working close or higher of that frequency. Well, so let's consider a commercial component. When you try to find a commercial component, you find that at some specific frequency, the manufacturer gives you the self-resonant frequency. So for example, for this inductor, it's an inductor of 2 microhenries. You can see that you have a core. For this inductor, the manufacturer gives us the information that the self-resonant frequency is close to 100 megahertz. That means that the inductor is inductive below 100 megahertz, and at frequencies higher than 100 megahertz is capacitive. So it's not useful for our purposes. So let's consider, let's consider we want to design a topology. I have selected a DC-DC converter, but we can do something similar with PFCs or any other of the previous examples I was explaining. Consider that this buck converter will be working with 24 volts. The output voltage is 12 volts, and the load resistor is around 5 ohms. So we have around 2 ohms, 2.5 ohms of current in the load. Okay. In my model, I will not have any kind of feedback. It's a very simple model of the buck converter, so you understand my idea. So we have here the input voltage. Here you see the switch. This is an ideal switch, and you can see here how is the control voltage for this switch. It's on off, giving a frequency, a switching frequency of around 500 kilohertz. We have a diode here, and we have the inductor. This is the main problem. This will be the main problem in our circuit. Look at this. In this simulation, the inductor is totally ideal. We have an output capacitor of 47 microfarads, and the output impedance is, like I have explained previously, 5 ohms. We run the test. You can see the square wave signal in the switching node voltage. This is the signal that usually is the origin of the harmonics we will identify in conducted emissions from this buck converter. You can see the output voltage is here. It's around 12 volts. And you can see in the plots on the right you can see the current in the inductor, the current that is going in this direction, and in the time domain, top view, and in the frequency domain in the bottom view. You can see the harmonics that are related with the ripple in this current. Obviously, all the activity of these harmonics is around the full PC board, around the full set of components, especially in the magnetic field we have around the inductor. So this is the ideal behavior of this simple buck converter. So let's see, we want to build this kind of circuit. So we go to the laboratory and we select a component. This case is a Texas Instrument component. So we have here the switch. Let me draw here. This is my main switch. You can see that from my ideal circuit, this is the input voltage. This is the output. This is the diode. I am using here a Schottky diode. We have here the inductor with core, and we have the 447 microfarad capacitor. And in the output, we have the 5 ohms resistive load. Okay. In my previous model, there is no model, or I am not modeling the feedback or the control circuit. Okay. So let's try to see what happened with this circuit in the laboratory. So we go to the camera. Let me show you the camera here. Okay. So this is my buck converter. You can see that I have here the 2 different buck converters. This is 5 volts. This is 12 volts. I am not using the 5 volts buck converter. The power is off. And you can see here the load for my circuit. It's a small fan powered by the 12 volts output of the buck converter. From using this input cable, I am introducing in the buck converter the 24 volts for our circuit. And I am measuring here the voltage in the output, and I will be measuring the common mode current in the input cable. Okay, so let's switch to the oscilloscope. Let's switch to the oscilloscope. And what you see here, really, I can show you with the camera how is the setup. Let me show you here. So with the camera, you can see what I am doing. I am sending the signal to channel number 1. In channel number 1, I have the voltage in the switching node. In channel number 2, I have the common mode current in the power supply cable. Here you can see my load 400. Okay, so let's continue with the screen of the oscilloscope. The screen of the oscilloscope is here. Oh, sorry, I was not showing the camera. Sorry. Here, okay? This is what I was trying to explain. Sorry for the mistake, okay? So you see here that in the channel number 1, I have the voltage in the switching node. Here is the common mode current, and here you have the load 500. Okay, sorry for not connecting the camera previously. So now let me show you the screen of the oscilloscope. It's an RDO oscilloscope, RDO 6. So in the top of the screen, you have the time domain of the switching voltage, and in AC mode, I am only interested in the ripple, in the noise we can have in the 12 volts output voltage. Here is the frequency domain, and on the right you have in the top trace is the time domain of the current probe, and in the bottom you have the frequency domain of the current probe. The frequency axis goes from DC up to 300 megahertz, and the scale is logarithmic. So this mountain you see here is the frequency modulation band, is radio, FM radio in my area. And you can see that I identify this energy. You can consider this is something like noise or some external noise in the ambient. So we will consider that this is not part of our experiment. My buck converter now is off. So let's consider that I switch on my buck converter. So let's switch on. So let me increase the intensity of the trace. Let's go to the intensity of the trace now. So you can see here, I have a lot of peaks of noise in the ripple of the power supply. I am using the probe with a big pigtail, okay? Like you have seen in my previous picture, no? You can see here I have a big pigtail, but for the purposes of this demo, this is not a problem for me. And you can see how is the frequency domain. You can see in both traces, in both results, in both FFTs, I have the same idea. The idea is that I have the harmonics of my switching activity, but suddenly I detect this kind of mountain. This mountain is around 200 megahertz, 120 to 300 megahertz is a mountain that usually is the main origin of problems of this kind of circuits in radiated emissions. Usually you will be injecting common mode current in the cable. The cable is a very long antenna. It's 1.1 meter, 2 meters, and this length in the cable make the cable a very good antenna for VHF frequencies. So when you are working with this kind of DC-DC converters, and you are failing between 100 and perhaps 300 megahertz, be careful about this kind of resonances that we have in our circuits. So let's consider what happened if we evaluate in our circuit how is the effect of the inductor. So here, let me switch off the DC-DC converter. I am going to remove the the inductor, okay? I have the inductor with several pins, so it's easy to connect and disconnect. And let me show you the screen of my both 500, sorry, instrument. Here at the input, you can identify, I am going to measure the impedance of the inductor in this accessory. You have a lot of accessories to make these measurements in a better way, but this is faster for my purposes. And let me show you the screen of the software here. Okay, so I'm going to evaluate how is the impedance of these inductors from 10 hertz to 550 megahertz. This is one of the advantage of the both 500 is that it arrives today up to 500 megahertz. And this is a very good range to evaluate this kind of resonances that are dangerous between 100 to 500 megahertz. No? In the vertical scale, you have the impedance on the left axis, and on the right axis, you have the phase. So let's connect the inductor to the device. I have calibrated the instrument to minimize the time for the demo. Okay, so the inductor is here, and let me show you again how is the response of the sorry, wait a moment. I can let me go here and let me make a measurement. Okay, initially the horizontal scale is logarithmic, is slow, but suddenly. So what is interesting here? The blue color is the phase. The red color is the impedance. You can see that the phase is 90 degrees when the component is inductive. This is the area where we are working. For example, if I take the cursor and I move the cursors to 500 kilohertz, let me introduce directly with my keyboard, 500 kilohertz. When we are in 500 kilohertz, the inductor is around, I don't know, 68 microhenries. That is around 211 ohms, and the phase is 90 degrees. For my switching frequency, the component is it's a very nice inductor. What happened at low frequencies? The phase tries to go to zero, and you can see that the response of the inductive effect is horizontal here. This is the resistive effect. Instead of going from zero, we must consider that the inductor has some resistance at low frequency. This is what we call at the end, this is the RDC value, no? When you increase the frequency, the resistance increase because of the skin effect. And this is the self-resonant frequency. Look at here. The phase is 0 degrees here, and the phase 0 degrees means that at this point, the inductor is resistive. So the component is going from inductive effect go to resistive effect, phase equal to 0, and suddenly start to be capacitive. And this is minus 90 degrees. And what is interesting from this measurement is this. From this measurement, what is interesting is that we have additional resonances. In this component, I have only one additional resonance that is important is around 200, 300 megahertz. And this is what can be very dangerous in your application. If you are working with PFCs, you are working with topologies, using transformers, using inductors, using analog filters, be careful about this kind of additional resonances, because in theory, this could be capacitively, but we have this very low impedance, no? Remember that in theory, what I was expecting is a component that increase impedance constantly, okay? So let's do something very interesting with this tool, is that we can go here and we can try to evaluate how is the best model for this component. So we go here and we access to the add circuit fit. When we click here, I'm sorry, what? Sorry, no, sorry, here. You don't see now my screen. Sorry. Let me see if you see the screen. I hope you see the screen now. Okay, so you see the screen, Florian? Okay. So you can select here the model that is better for you. Obviously, we can select different traditional models for crystals, for different components, for inductors, simple inductors. But I'm going to select not this model. I will try to use the network. In the network, I can model complex networks, no? And then I start the process of fitting the model, no? So automatically, what I get is a model that is basically trying to follow the response of my circuit, no? You can see here the schematic, you can see here the components, no? So the idea is that with this model, I can export a netlist. And in the netlist, I create a .cir file that is a typical SPICE model for the inductor, okay? When I have the model that is matching what I like, I go here and you can see, let me increase here the thickness of the trace so we see this better. You can see here how the model in the dashed line is following the response of the measurement. No, the model is so good compared with the red trace that is difficult to see. So let me decrease the thickness of the red trace here, so you can see that the model is following exactly the response of my circuit. So now what we can do is we can go to the SPICE screen. Let me go to the SPICE screen now here, and we can open a circuit file open that I have in my computer. No, in my computer you can see I have two different LTSPICE circuit. The first one is model test. What I am doing here is this. What I am trying to do here is to compare how much is the impedance of an ideal 68 microhenries compared with the model we are creating. Sorry, this is Inductor is from Coilcraft. Okay, so let me go to the component menu, and let me select the subcircuit symbol for my component, and let me go here to the model we create with both 500. Let me go here, and we open with the notepad. Okay, you can see here, this is the model I have created with the both 500. We copy, and easily you can paste here in this way. So now this component, circuit-fit-1, is modeled with this subcircuit model in LTSPICE, circuit-fit-1. Okay, you can check that this model is the same like in the schematic from the both 500 software, and we can run the test. We are going to run from 100 Hertz to 500 megahertz. So now, sorry. Inductor SPICE model. What is this? Sorry. Wait, try to do this. happened? User simulation. Okay, why it's not? Wait a moment, please. Let me try. Sorry, this is the typical situation with.
Live demos?
No. I haven't no, it's the idea of the different parts. Let me try if I now correct. Okay, so now you can see how is the response. I am.
Arturo, we don't see the full screen. Maybe you can zoom out a little bit.
Yes. You see now better? Okay.
Yeah, I'm not sure. Maybe something is.
Okay, well, don't worry. Wait a moment. We solved the problem very easily. LTSPICE, this one. Okay, let me make some change. I don't know why it's not taking the full. Fill it vertically. This way. You see, oh, I don't know why it's, let me try. I don't know why it's reduce it. Anyway, let me show you here. This way. Okay, what you see on the left, is my circuit with the model. I have started with body 500, and see here you can see the comparison between the ideal and the model we are measuring. You can check that in black color is the ideal component, is 68 microhenries ideal with 90 degrees in phase, and in red color you have the phase and the module of the impedance, where we find that at low frequency we have a resistive effect, we have the self-resonant frequency, and additionally on the right we have the resonance, we have around 200 megahertz, no? So this is only to check that the model is correct. When we have the model correct, we can go to the here. Let me go again to the second file. That is, my file is, let's go here, simulation, here. I go to the second model, and in the second model, what I have is the same ideal buck converter I was designing previously. Let me go. It's here. Okay, we have the same ideal circuit, but in the second part we have the same circuit, but with the model we have just tested, and then we run the test. Let me run the test, and let's see what happened with the response of the circuit. So let's put this in vertical. Let's see if we can put in the screen correctly so you see perfectly. Let me move this here, here, and here, this way. And now let me run the test to see, for example, how is the current in the inductor. Okay, let's go to see how is the current in the inductor and how is the current in the real inductor, real relative. Okay, so you can see that the ripple in the current is triangular, and here we have a triangular response. They are close in magnitude. The magnitude of the current obviously is related with the duty cycle you are using for the switching activity. But what is interesting is to see how is the FFT of these traces this way. Okay, so we will try to evaluate from the FFT of this buck converter. How is? Let me go here. Let me take some setup. We go here. We select the two currents, and we can compare how is the spectrum. Okay, you can see how the red, the black trace, the black waveform is the spectrum of the signal in the ideal buck converter. The red color is the result of the simulation using the model we have extracted with both 500, where we can see that for the same ideal topology, the spectrum of the harmonics is similar, but we have a broadband emission close to the 200, 300, 100 megahertz. And this is the emission that is related with the behavior of the common mode and with the emissions we detected in our in our measurements. Okay, these emissions here, this mountain we find here, is the same mountain we are identifying in our simulation. So this is the idea of the presentation I was trying to show you, and let me know if you have any question. I hope you found interesting the process of taking your inductor, your transformer, your component, to check how it's working up to 550 megahertz, and to remember that with this kind of models, you can identify, or you can check how your emissions match with the internal resonances of this component.